Welcome to the review for chapters 9, 10, 17, 18, and 19. This is going to be the review for exam 3. We're going to be doing these 5 chapters, and I know 5 chapters seems like a lot, but especially in 18 and 19, there's really not all that much material that we're going to cover. The exam is going to be predominantly 9, 10, and 17. But with that being said, let's go ahead and just jump in here and start talking about what the exam is going to cover. So in chapter 9 here, actually let's just do it this way. So in chapter 9, we start off here talking about waves. And I do expect you to know just generally how to describe a wave. You should recognize what a wavelength is, what the frequency of a wave is, and the speed at which a wave can travel. So just being able to tell the difference between those 3 things. You do not need to have memorized what the speed of light is or what the speed of sound is. That cheat sheet that I give you with every exam actually already has the speed of light on it. So you don't have to have that memorized. Let's see, I do expect you to know that frequency and wavelength are inversely proportional. So as one of them increases, the other decreases. So light that has a very high frequency has a very tiny wavelength, and things that have a very large wavelength have a very low frequency. As far as all this section in here talking about the different kinds of light, all I expect you to know is that UV and above, so to speak, from UV up to higher frequencies, they can damage tissue. That's really the only thing I expect you to know. So gamma, X-rays, and UV can damage tissue, and the rest of them cannot. Okay, so then we got into the Bohr model here, and the Bohr model was really just kind of a gateway for us into understanding how electrons behave and how to describe electrons. I'm not going to have you writing or drawing Bohr models or anything like that. Like I said, this is just kind of an introduction into the idea of electrons. Same thing with Schrödinger's equation. I'm not going to have you solving Schrödinger's equation, obviously. You would need to be in a graduate level chemistry course to be solving Schrödinger's equation. I only did that a few times when I was in school, and it was unpleasant, so I'm not going to make you do it. And actually, it can only be solved for very, very simple situations anyway. Alright, so now we're getting into some more stuff here that you do need to know. You do need to know the quantum numbers, or more specifically, how to assign quantum numbers to electrons. So this whole section in here, where we talk about the quantum numbers, we talk about how they're essentially a filing system in the atom, we talk about all the shapes and the relative numbers of the different orbitals inside subshells. All this stuff really culminates, and then also here with the correct order of subshells, it really culminates here, where we were actually writing electron configurations. And you will be expected to write electron configurations on the exam. Now, the way this is going to work, you're not going to write the entire electron configuration. I'm going to have the question set up where essentially you just have to put in the correct number of electrons. Now, this is by no means ideal. I really wish we could have a paper exam here where you could actually write out the electron configuration or write out the orbital diagram, and there's just really not a good way to do that in Blackboard. So the way these will work is I will have essentially this type of thing already set up. I'll have the base electron configuration already in and ready to go. We'll have the 1s, 2s, 2p, and so on and so forth. So I'll have, the correct ordering here, and then I will give you an element, and you will have to put in the electrons. So you would fill in the superscripts, essentially. Now they won't look like superscripts when you put them in, but that's the best way I could come up with for doing electron configurations in Blackboard. There's just unfortunately not a better way of doing it. I do expect you to recognize the difference between core and valence electrons as well. So that would be a relatively simple question. I could give you an already created electron configuration, and the question would just be how many valence electrons are there, how many core electrons, and so you would have two numbers to fill in. Okay, and so then the last thing here is the periodic trends, which were related to the electron configurations. And so I will ask you some questions on periodic trends. The way that those I normally ask those is I will give you a pair of elements, like maybe helium and neon, for example. Say here are these two elements. Which one is larger, or which one has a higher ionization energy? I'll pick one of the trends that we talked about, and you will have to tell me which of the two has a larger amount of that property, or have a larger value for that property. So there will be some of those on the exam as well. So make sure you know how to identify which elements are higher for each of these different trends that we talked about. Okay, so that is Chapter 9. Chapter 10 is mostly about Lewis structures and via CPR, if I remember correctly. You definitely need to know how to draw Lewis structures, because there will be Lewis structures on the exam. Now, once again, there's not really a good way for me to have you draw a Lewis structure in Blackboard, in the software. So the way that I'm going to do this, because again I told you, you will need to draw Lewis structures on the exam, I guarantee it. The way that I'm going to do this is I'm going to give you a molecule. So I'll give you the formula for a molecule, like maybe SO2 or something like that. And then the way the question will be stated is, in the best Lewis structure for this molecule, identify how many of the different components it will have. So I would give you SO2, for example, and then you would draw the best Lewis structure for SO2, and then in the question it would have a spot for and it would specifically say on the central atom. So how many of each of the following things would be present on the central atom. And so it would have a spot for single bonds, a spot for double bonds, a spot for triple bonds, and a spot for lone pairs. And so you would have to fill in how many of each of those things were attached to the central atom. Now again, this is not ideal by any means, but it's the best I can come up with for testing in Blackboard, and still essentially requiring you to actually draw the structure so that you can see how many of each of those things are in there. So if you had something like methane, for example, let me see, like this here. So in the question, to answer that, you would put 4. So again, there'd be 4 different spots to put in a number. One for single bonds, one for double bonds, one for triple bonds, and one for lone pairs. You would put 4 into the spot for single bonds, because methane has 4 single bonds on the central atom. and then you would put 0 for all the rest. And you do actually have to put 0. You can't just leave them blank. If you leave it blank, I will assume that you mean 0, but you're just making more work for me, and you don't want to make me cranky while I'm grading the exam. So put in 0s because it will then grade it correctly, and I won't have to go through and manually grade those. So if there are none present, put 0. And so that's how I will handle Lewis structures. And there'll be a few other questions, most likely as well, just kind of random things about Lewis structures, like just very general knowledge, like if you have a line, what does that represent? It represents a bond that has 2 electrons in it, just kind of little things like that you should already know, assuming that you can draw Lewis structures correctly. Okay, so then the other big topic here was VSEPR. This again will also be on the exam. The way that I ask questions over VSEPR, because again I can't have you drawing stuff, is I will either give you a Lewis structure, kind of similar to what is happening here in these slides. I'll either give you an already completed Lewis structure and then give you multiple options for you to pick the correct VSEPR structure, or I will just give you general information. And so I might say, you have a structure that has 2 lone pairs and 2 bonds on the central atom. What would be the molecular geometry for this molecule? So I'm not giving you the Lewis structure like you have here, but that is more than enough information to work out what the geometry is. So again, if you have 2 bonds and 2 lone pairs, that would be a bent molecular geometry. So I will either just give you a Lewis structure, or I will give you the information on the groups so that you can work out what those geometries would be. And so again, you would just be picking the correct geometry from a list. I don't think I had any where you had to write in the answer yourself. It should just be picking from a list. And I will give you this this table, by the way. I'm nice like that. So you do not have to memorize all the different names. You just have to know how to use the table. Oh yes, and I did forget about this. So I will expect you to be able to identify polar versus nonpolar molecules as well. So this is actually the last main topic of this chapter. So when it comes to polar versus nonpolar, the main thing here is being able to recognize that a bond is polar, and then secondly, being able to recognize if the molecule itself is then polar. So I expect you to be able to do that, and so once again I will give you the electronegativities if you need them. So here we have a nice little table that you could use. I'll either give you this one or one that has the same data. But you should be able to determine if a bond is polar. If you remember, the cutoff for that is 0.4. So if the differences between the 2 electronegativities of the atoms in the bond is greater than 0.4, then that is considered polar. And if the difference is 0.4 or less, that is considered nonpolar. So I expect you to be able to tell, and if I remember correctly, a few of the questions that I put in are just as simple as that. Just, you have this atom bonded to this atom, is that a polar bond? And so you need to be able to answer questions like that. And then also, you should be able to recognize if the molecule itself is polar. Now I won't do anything super tricky here. I'm not going to give you a molecule that looks like it's symmetric when it's actually not, or looks like it's not symmetric when it is. It should be fairly obvious if a molecule is symmetric or not. So if you have polar bonds with a molecule that is not 100% symmetric, so again, it's not good enough for it just to be symmetric along one axis. It has to be completely symmetric. If it is completely symmetric, then it cannot be polar. But if there are any modes of asymmetry, then it will be polar, assuming that it has polar bonds. Now, obviously, if it doesn't have polar bonds in the first place, then it can't be polar. But if you have polar bonds and the molecule is not 100% symmetric, then the molecule itself is polar. And again, I will not do anything tricky. It should be fairly obvious if the molecule is not 100% symmetric. And if the molecule is 100% symmetric, again, it should be fairly obvious. I'm not going to draw a molecule in a strange way that so you're not completely sure. Like, it should be very clear. All right, so that is chapter 10. So let's talk about nuclear real quick. So in the nuclear chapter, stuff here at the beginning, just kind of an introduction. But here at this point, when we talk about the different types of radioactive decay, I do expect you to understand what's happening in each of these different kinds of radioactive decay. So that would be alpha decay, beta decay, gamma radiation or gamma decay, and then positron emission. So I do expect you to be able to identify when each of these things are happening, as well as fill in or write different nuclear equations like this. And usually, if I remember correctly, the way that I asked these questions was I didn't have you writing an entire nuclear equation, just because that, again, my limitations with Blackboard. Instead, what I would have you do is I would give you part of an equation. So maybe, for example, this one here, I would show you the radon, and I would show you the beta particle, and I would block this portion out, and then I would have a spot where you would fill in the mass number, the atomic number, and then the symbol that would fill in here. So you wouldn't actually write it into the equation itself. There would be a spot down below where you could put in those three things. And they would be labeled. So there'd be a spot that would be labeled mass number, spot labeled atomic number, and then a spot labeled atomic symbol. And so you would fill in what was missing into those spots there. So do know how to write nuclear equations, or at the very least fill in blanks in a nuclear equation like that, because you will need to do that on the exam. I also expect you to know the relative ionizing and penetrating power of these. Thankfully, this is pretty straightforward because those, again, are inversely proportional. So alpha particles, which are very highly ionizing, are really bad at penetrating. Gamma rays, which are really still dangerous, but relative to alpha particles, have low ionizing power, are really good at penetrating, and then the positrons and betas are in the middle. As far as the strong force here, really all I expect you to know is that the strong force is what holds the nucleus together, and that's it. So the strong force holds the nucleus together. As far as half-lives, I do expect you to know how to use a half-life, but it will be a very, very simple question. If I remember correctly, there is a question on the exam where you will deal with the half-life of a nuclear decay process. But again, it's going to be very simple. The math is just going to be whole numbers of half-lives. So we're not going to have like a question where 1.83 half-lives have gone by, and you have to work with those numbers. No, it'll be whole numbers of half-lives. So I could say you have some molecule, you start with 10 grams, and it has a half-life of 10 minutes. If 30 minutes goes by, how much of the 10 grams is left? Well, if it's, and those are obviously really simple numbers, but it'll be similar to that, where, that's 10 minutes for every half-life, 30 minutes have gone by, so that's 3 half-lives. If you started with 10 grams, the first half-life, you would only have 5 left. Second half-life, you would have 2.5 left. And then the third and final half-life, you would have, let's see, what would that be? 1.25 grams left. So it would be something like that, where it's whole numbers of half-lives. And you would just work out, okay, how many half-lives are in that period. So then take how much mass, divide it in half, that many times. So it would be a simple example like that, with whole numbers of half-lives. Okay, so these radioactive decay series, I'm not going to have you doing anything with those. As far as the natural sources of radiation, the only thing I expect you to know here is that radon is the main source of nuclear exposure for people. Detecting radioactivity, I'm not going to have you describing dosimeters or Geiger counters. I don't think I'm going to have you describing any of this stuff either. So this is just more of talking about the different applications of nuclear processes. Right, so then let's move on to our last 2 chapters here. So chapter 18 is organic chemistry. And this whole chapter is pretty much the same throughout. We just talk about different categories of organic molecules and about their general chemical properties. So what I'm going to have you do for this chapter, and it'll be pretty much the same for the next one as well, is any of these big categories that we talked about, you need to be able to identify those molecules. So, for example here, we had hydrocarbons, and we split those up into alkanes, alkenes, alkynes, and aromatics. You should be able to identify all 4 of those. And it's pretty straightforward to identify these. And you should also be able to identify saturated versus unsaturated. So if I were to give you this molecule, for example, I could just cut and paste this image, and crop it down to just this molecule here, and I would then ask you classify this molecule, and I would give you the different options. I would give you alkanes, alkenes, alkynes, and aromatic, and you would have to classify this and say that is an alkane, and we know it's an alkane because you have only single bonds. It's just carbon and hydrogen, and there are only single bonds. So that is an alkane. And so then, I could have something similar where I cut and paste one of these. That would be an alkene because you have a double bond. These would be alkynes because you have a triple bond. And then if you have a ring structure, that would be aromatic. So just being able to look at a molecule and recognize that it's an alkane, an alkene, an alkyne, or an aromatic. I do expect you to be able to do that, and I will ask you to do that. Same exact thing with these functional groups. So you will need to memorize what these functional groups look like. Thankfully, there's not very many of them here. There's only 7, I guess. Yeah, 7. And they are all different. Some of them do look kind of similar, but they are all different. So I would expect you to be able to identify these 4 functional groups. So I could give you a molecule like this, for example. And I would give you, the multiple different options to pick from. Aromatic would not be one of the options because this is actually an aromatic. So in this one, it would just be the different functional groups that you would have to pick from. And you would have to recognize, oh look, there is a carbon with a double bond to an oxygen that is then also bonded to a hydrogen. That's an aldehyde. Similarly, over here we have a carboxylic acid because we have a carbon double bonded to an oxygen, and then that is single bonded to an OH. I would find something that doesn't have another OH here, by the way. Technically, this is a carboxylic acid because the carboxylic acids have priority over alcohol groups, but we didn't really get into priority and stuff like that. So I would find a molecule where the carboxylic acid was the only thing in the molecule. So just being able to recognize all of those. And then obviously if there's a nitrogen, it's just an amine. As far as the polymers, don't worry about those. I'm not going to test you over the polymers. So then, in a similar fashion with the biochemistry, we had 4 big types, I guess you can call them, of chemical components that we looked at. And the main thing here is going to be identifying the different kinds of molecules here. So with carbohydrates, I will expect you to be able to recognize monosaccharides versus disaccharides versus polysaccharides. So monosaccharides, those were just a single sugar molecule. Di had 2, and then poly has more than 2. So I expect you to be able to identify those 3. And remember, the easiest way to tell that it's a sugar is lots and lots of OH. If you got OH all over the place, it's probably a sugar molecule. Lipids, kind of the same thing. Should be able to identify lipids just in general, but then also be able to identify saturated versus unsaturated. Mainly triglycerides here. So we have, here's a saturated one because there are no double or triple bonds anywhere. And then down here we have an unsaturated one because we have those double bonds. And by the way, you don't have to have those on all 3. If there's even a single double bond, it is unsaturated. You should also be able to identify phospholipids. Again, this should be pretty straightforward because it's the only thing that we saw that had phosphate in it. So if you see phosphate, it's a phospholipid. And then steroids, kind of the same thing here. So steroids, if you recognize this shape, then you should be able to see, okay, that's a steroid. Proteins, I do expect you to be able to recognize or recognize an amino acid and the different parts of the amino acid. So you have the amine group, the carboxylic acid group, and then the R group, the thing that makes that amino acid unique. I will not have you memorizing these, though. I had to memorize these, but I was in a senior level biochemistry class, and this is not a senior level biochemistry class, so you do not have to have those memorized. But I would expect you to just recognize an amino acid if I gave you one. More importantly, though, I do expect you to be able to recognize the 4 different tiers of protein structure. So primary structure versus secondary structure versus tertiary versus quaternary. So if I were to give you a helix like this, or a pleated sheet, I would expect you to be able to tell me that that is an example of a secondary structure. And if I were to give you something like this, where you have multiple chains interacting with each other, that would be a quaternary structure. Okay, so this is just talking more about those different kinds of structures. Obviously, I'm not going to have you drawing any of these or anything like that. It is just going to be recognizing them and identifying them. Okay, so then the last thing here is with the DNA bases. I do expect you to know which DNA bases pair up. So A and T are always paired, C and G are always paired, and I expect you to be able to make a matching set of DNA. So if I were to give you this, for example, ATGAATCCGAC, and if I were to ask you to make the corresponding acid-base pair chain, I would expect you to make this. Obviously, you wouldn't draw it or anything like that. You would just write out TACTTAGGCTG. Just match each of the acid-base pairs in the first string with their partner. And so I do expect you to be able to do that. So expect to do that on the exam. And I believe that is it. Yeah, so here we're just talking about replication, which is kind of a similar topic there, about creating the matching strand. And I'm not going to test you over mRNA or anything like that. Okay, so there's a lot of topics here for this exam, for sure. But none of them are super intense, at least in my mind. I know I tend to see things differently than brand new students, but mostly just because of the limitations of the software. I can't really have you do too much on any one question. So if you have any questions about the topics that we talked about here, if you have any questions about how I will ask questions, feel free to send me an email, and good luck with your studies.